Can I start, sir?
Wait. I think it's working. So
Oh, Mike.
Dr. Predam, you can start now.
Okay, sir. A very good evening to all of you. Now I am going to introduce our next speaker, Mr. Jonathan Vellore. His invited talk is on aerosols for water filtration. Mr. Jonathan Vellore is an interdisciplinary scientist presently working for a PhD in water filtration using biopolymer aerosols at the University of Plymouth in the UK. Using graphene oxide for filtration purposes became the greatest challenge. This took the work from 2 dimensions into 3-dimensional aerosol structures that are biodegradable and biocompatible. Jonathan has been awarded first prize for a poster at the first International Aerosol Conference at Newcastle University in the United Kingdom, and was also selected for a Junior Research Exchange Scholarship to collaborate with IIC Bangalore. Now I am requesting Jonathan, sir, kindly proceed with his presentation.
Fantastic. Thank you. And thank you, VIT. And thank you very much for your invitation to talk today. I'm going to share my screen. Everyone see me okay? Just good? Yep. Okay, great. Well, I'd like to welcome everyone to my talk here. My name is Jonathan Vellore. I am from Plymouth University in the UK. And it's really great to be speaking here at VCAN 2020. And once again, yeah, thank you to the team there for inviting me to speak. It's been a very, very interesting couple of days. I've really enjoyed participating, and let's kick off. So today I'm going to talk about my research at Plymouth. It's graphene oxide biopolymer aerogels. So let's get started. Okay, that's it. So let's just run through some of the contents of today's talk. I'm going to talk a little bit about some water issues, and then which we both share here in the UK and in India and across the world. And then to look at some traditional solutions that are still being used in both countries. And then really to sort of focus in on how we can use nanotechnology as a solution for cleaning up water. And in particular, graphene oxide as an emerging nanomaterial. Then I will talk a little bit about where that took me into aerogels themselves and what they are, and how we fabricated those. And then we'll be looking at some applications of aerogels and our overall vision. And part of our overall vision here, as you can see, is having beautiful rivers like this where you can drink the water, and there's flora and fauna and fresh fish, and trying to prevent situations like this on the bottom. So water issues, let's have a look. So toxic metals are a big part of our work here at Plymouth. We've been looking at, we suffer from toxic metals in the water here due to mining. In the next county along in Cornwall, there's arsenic in the water. We've also had, historically, we've had lead in the water due to sort of pipes and general fittings within water supply. And this is a nature of plumb solvency. So, as the water becomes more acidic, you're going to leach out more lead into your drinking water, which has been an issue. We'll also be looking at oil contamination a little bit. Organic dyes a lot of organic dyes comes from the fabrics industry, so we have a lot of that washed into the rivers, causing lots of problems. And in some places, the salinity is a big problem, where you have, well, particularly as we look at this graphic here, you can see that when we talk about fresh water, we forget that yes, the world is covered in water, but only the 3% that is fresh is then split up into its relevant parts. And ice caps, glaciers is holding a lot of that fresh water. Groundwater is a big contributor to our drinking water supply. So preserving this and maintaining this is really, really important. So So yeah, so when we talk about salinity, you know, we get, when we deplete groundwater supplies, we get a kind of pressure gradient between the sort of ocean and then the porous rock in between, and then this kind of starts to turn this fresh water into brackish water, and then causes, you know, problems for drinking and using for agriculture. So this is, you know, so groundwater is a big issue, really. Microplastics are everywhere. We may touch on this a little bit, but these, and there's also contaminants of emerging concern. So, you know, we've got persistent organic pollutants, we've got endocrine disrupting chemicals, you know, so there's a lot to be thinking about in the future, and particularly groundwater. So, and you can see here rivers. I mean, we think we drink a lot of river water. Well, we actually probably don't. So it is said that there's going to be 4 billion people in water stress by 2030. Now that's not a long way away. A lot of people are in water stress right now. It's a critical issue. As I say, we're pretty much focused on toxic metal pollution throughout this PhD, and in particular lead. I know there's lots of problems with arsenic throughout the Indian subcontinent. So, you know, these issues, and even, I mean, even in somewhere like the US, you know, where they changed their supply from Lake Huron to use a new water source for Flint, Michigan, they ended up, you know, unfortunately, releasing a lot of lead into the supply there, which caused, you know, major health problems. So it's not just, you know, places with good infrastructure have problems also. And, you know, we can solve things, we can solve problems with good infrastructure. If we change all of our lead pipes, if we have, you know, relevant raw water treatment works, relevant wastewater treatment works, then we're, you know, we are able to mitigate and remediate some of these problems. Now, a lot of places don't necessarily have infrastructure, or, you know, the infrastructure is poorly managed, which can lead to breaches of, you know, guidelines and regulations. Now, so to combat this, pretty much this non-functioning infrastructure, and also the cost of putting something in, we were looking at low-cost portable solutions, and we know that a lot of people already rely on reverse osmosis as a way of treating groundwater, which, you know, is not accessible for all people. So and it also has a sustainability issue, as it produces, you know, much more, you know, a waste brine, or a waste, you know, a waste quantity of water for every liter of fresh water that you drink. You get sort of 5 liters of you know, concentrated wastewater. So it's not necessarily sustainable, reverse osmosis, but, you know, so traditional solutions that we've really, you know, that we've all seen, you know, across the world. I mean, we still use reeds in the UK for road runoff into lakes and river systems, sand. There's pebbles in wastewater treatment works. We've used ceramics, ceramic filters. There's natural zeolites for absorption. I know that when I visited India, there's, you know, often seen water in copper vessels for you know, microbial prevention, and the use of, you know, biochar made from coconut husk, or, you know, your standard activated carbon, which can be bought commercially. Now, these are small scale solutions, and they're often put into some sort of gravity fed system, and out the other end you get a reasonably good result. But some of the sort of recalcitrant sort of metals, especially, can you know, not be removed by this process. I mean, here in the UK, powdered activated carbon is used as an infrastructure solution, which we don't regenerate. It goes off as some sort of sludge, and then it is landfilled. Granulated activated carbon is regenerated, and depending on the type of geography and the water supply, that can be implemented in raw water treatment. Now, AC, it's a great thing, activated carbon. I mean, and that's why it's kind of like the last line of defense, really, because it's got a fabulous specific surface area, and lots of binding sites, you know, for organic molecules and heavy metals to bind to. So you know, and some of the problems with especially using powdered activated carbon is this agglomeration in the treatment process, where you can then be obstructing its surface area somehow, and that's often with the presence of natural organic matter. So that can prevent the efficiency. So we're looking to sort of try and improve efficiency using nanotechnology. So this is a kind of general scheme of how AC works. You've got this fabulous carbon matrix. You've got 300 to 1,000 nanometer pores. You've got a variable pore size, a good surface area, 1,000 square meters, and this kind of non-uniform structure, which, you know, isn't necessarily a controlling aspect to your filtration process, but still it's highly effective. So the kind of the size of contaminants that we're looking to remove, the metals in particular. Now, this is a nice little graphic here from DEFRA in the UK, and you know, we're all down at this end of the scale bar here, the metal ions, aqueous salts, and you know, we're looking at pretty much reverse osmosis nanofiltration. These, you know, high pressure, high energy solutions to removing, you know, sub-micron contamination. And we here at Plymouth are thinking, well, okay, this is great. This may be a solution for a lot of people, but it's not necessarily a solution for rural areas and for people that can't necessarily afford to have RO installed in their house, or don't have access to boreholes that can then be fed into an RO system. So we took an overview of raw water treatment and tried to look at how nanotechnology can help this. And this was a kind of schematic that we came up with. We've got this raw water here in the UK, particularly surface water, and then we've got the screening that goes on. And then in orange here, we have these potential places where we could use new nanomaterials to influence and improve the water treatment process. So adding nanoparticles, for example, here in the rapid mixing, to improve floc formation or coagulation, so we have a better settling out of contaminants. And this is a particular area of interest for us, you know, as again, we still use sand, we still use gravel. They're great barriers in this multiple barrier principle. And again, you know, GAC is there. So we really like this area to focus on, really, as our kind of, how do we get nanomaterials into water treatment, not only here as a kind of, you know, not only here in the UK, but this particular point, once you've done all of the large filtration and the large screening of the water, you know, it looks clean, it's been through gravel and sand, but there are still toxic metals in there which are causing health problems. So this is where we really focused on. And you know, this is a kind of non-exhaustive sort of mind map diagram of the three, you know, sort of potential routes for nanotechnology, and in particular, you know, absorption became our kind of focus, as it's, you know, it's highly effective, you know, for large volumes of water, for high flux rates, and can be, and you know, and sort of, you know, is the most cost effective. Although we do have some, you know, filtration going on now, and just up the road from me, and a new sort of ceramic ultrafiltration that's supplying Plymouth with water, which has just come online recently. So this type of filtration is also being implemented in the treatment of raw water. But incidentally, the local people didn't like the taste, but you know, it's taken a bit of adjusting. But let's get back to this. You know, this is where, so we like carbon, we like carbon-based materials, but we wanted to improve this accessibility to this, you know, the kind of the pores and the surface area that carbon can really do. And so and when we think of carbon, we think of, you know, most of us in the nano world these days think of graphene and graphene oxides. So this has been a kind of like the instigator of our research here at Plymouth. And as we had a talk earlier in the week by Dr. Guy in their fabulous talk about his new sort of construction of nano capillaries and the transit of ions through these capillary structures. Now this is, you know, this is from their research group many years ago now, 2012, where you've got this really interesting transit of water through graphene oxide membranes, and then a kind of rejection of helium at the same time. And how, you know, how is this possible? You know, helium smaller than water, why is it, you know, et cetera, et cetera. And the key thing that came out of this research and that we picked up on was the swelling of the layers, the interlayer spacing between graphene oxide sheets. You know, when you make a graphene oxide membrane, if you do it by vacuum filtration or layer by layer assembly or something like that, you start to get there's an interlayer spacing, which is being kind of, I suppose, kind of the layers are being held apart by the functional groups that are there in the graphene oxide. So this interlayer spacing, you know, allowed for the water to sort of to filter through the membrane and be released, but would stay tightly closed as a result of there being no hydration, as this hydrophilic nature of the functional groups would you know, allow the swelling to come about. So this is, you know, this is another kind of graphic of research around that time. And, you know, we're always thinking of using graphene to filter water. We're going to make these identical pores that we're going to control, and it's going to be this kind of a molecular sieve. And, you know, there is molecular dynamics simulations out there saying that this is completely possible. And there are also research groups out there across the world that are able to control, to some degree, pores within pristine monolayer graphene. Now, anyone that works with pristine monolayer graphene knows how difficult it is to work with initially anyway. So we struggled a little bit to sort of, you know, go down this route. And we also were very interested in this kind of intercalating between layers of water with the contaminants, with the salts, with the metals. We also noted that, you know, because of these issues, RO was going to incorporate graphene oxide as a surface coating on the traditional polyamide filters so this would improve flux, hopefully improve the sort of the rate of sort of having to the biocidal aspect to it, where, you know, you'd have to sort of reduce the chlorination frequency to protect the polyamide structure. So, but ultimately flux rates are a problem, because, you know, with any, you know, any kind of sieve type filter, you're going to sort of eventually kind of block your pores, as it were. So interlayer filtration, standard filtration, or something else. And we wanted a kind of combination of the two. And this is where, you know, we came across the idea of using aerogel structures. Now, whether you're familiar with aerogel structures, a stock photo there at the top, you know, they're basically very low density solids. And these low density solids are full of pores. I mean, we're talking really low density here, you know, and we're not making aerogels of this sort of density, but they have a huge specific surface area to the volume ratio. So they have that real kind of characteristic of activated carbon. So we've, you know, this is fabulous. So we've got a surface area, we've got a surface that can be potentially functionalized in some way. So we're still looking at this absorption mechanism to remove your material, and you know, there's multiple applications that aerogels have been used for. And it's quite interesting, because, you know, using graphene oxide as a filter or a membrane, if you make a graphene oxide membrane, you know, it's hydrophilic membrane, you know, restabilizing that once you put it back into the water is quite a challenge. You know, you need to sort of you need to do some sort of functionalization of the surface, cross-linking of the surface. Otherwise, your membrane dissolves again, as it were. So we looked at aerogels, some little micrographs here of the cellulose and graphene oxide, and you can see pretty uniform pore size. So this is, interesting stuff. So how do you make aerogels? Well, our very simple process here, because we want some sort of low cost solution here. So we work with a precursor solution using biopolymers. You can use cellulose, pectin, alginates, and we wanted a functional nanomaterial to add to that. So we opted for our poor man's graphene, as we like to call it, graphene oxide, and we've got a graphene oxide solution here. And then this goes through hydrolysis and condensation reaction, and you get some nucleation points of the colloids, which then start to link together to form this network. And this is your transition from a solution to a gel. And as you leave this gel to age, the network strengthens and becomes more robust. And there's lots of techniques to sort of increase the strength of your network. And then you've got a drying technique, and we opted for a freeze drying technique. And we'll talk a little bit about drying in a minute. And this is an early, nice, fuzzy-haired aerogel of my own, very first attempt. And yeah, it's. I think this is probably this may even be without a biopolymer. So you could make graphene oxide aerogels, pure graphene oxide aerogels, but they're not very robust. So it's good to incorporate a biopolymer of some sort. Now, the reason we here are some of our now finished aerogels that we use for our heavy toxic metal remediation. Now, the great thing about the aerogels is you don't have to rely on a structure and the functionality separately. They're combined in one. It's an in situ synthesis of the structure and the functionality. So you kill sort of two birds with one stone, as it were. And there's it's not a kind of a clumsy sort of layer by layer sort of deposition of a membrane. It's an anisotropic structure that kind of naturally grows chemically. So this is that sol gel chemical reaction is really kind of interesting. The way that you can control the pore size, you can control the functional surface, and this cross-linking between, as I mentioned before, cross-linking graphene oxide with a biopolymer, this adds this double network for robustness. So you can actually physically handle and do something with your filter once you've got it. Now, we were kind of keen to make these filters carbon's a good biodegradable material. It's biocompatible, but also your biopolymer is also important in this, so you don't create more pollution, more secondary plastic waste, more bits that can fall. If it does break down and fall off, you won't have in the wrong places. You'll only have the contaminant that you've absorbed being released, rather than the contaminant plus another contaminant. So this is key to our kind of like our thinking, really. Another close-up of they're very robust. You can squeeze these aerogels. They're like a little cloth, really, like a little face cloth, and the wetting comes out. The wetting re-inflates the structure, and this is highly robust. So from this sol gel process, the drying techniques that we opted for purely for economy of scale and ease is this freeze drying technique. Now, traditional aerogels, if you could look at the history from 1931 and Kistler's work, you've got this critical CO2 drying technique. Now, the reason why drying is really important in aerogels is that you've got a sol gel, and you want to take the sol gel to a dried structure, and you need to get the solvent out of the structure, but you must try to preserve the pores and the structure of the material. Now, drying ambiently, it's called zero gel, you get a lot of shrinkage, you get a lot of collapsing of the pores, you lose the functionality, you lose that flux, you lose that carefully chemically designed porosity. Now, supercritical 2, you can take, if you take your monolith into a supercritical CO2 dryer, you can then move into the supercritical phase, and then you can prevent crossing that boundary between liquid and gas. You know, you can exchange these two phases without creating the capillary stress on the pores and preventing collapse. And a similar thing happens whilst freeze drying. I mean, the only difference, I think, with the freeze drying, I mean, you're sublimating the ice, but you have an influence of ice crystal growth when you freeze your sol gel in the first place. So this influence is quite can be quite considerable. So you have to be careful about freezing and how you do it, and there's a sort of chemical ways to sort of manage that, and we do pretty good on that, really. We don't have too much, because you can see it's pretty uniform. There's not really a kind of a sort of a fracture of the structure there due to the freezing process. So, and as I talked about, if you want to make monoliths with supercritical CO2, a great place to start is just to use your lab-based EM electron microscopy critical point dryer. So that's not a problem here. And but we freeze dry for the sake of economies of scale. So what sort of applications are we looking at here? Well, we have been particularly working on absorption of toxic metals and lead in particular, which we'll talk a little bit about in a sec. I have also done some pilot studies for oil water separation, which we continued over at IISc in Bangalore. We were incorporating the aerogel structure to make a kind of a layered aerogel plus nanofiber coating to see if we could then get a multiplexed filtration system, and I'll show you some results from that in a minute. We also did some cationic dye absorption, in particular methylene blue. So these are the sort of work that we've done, but there's places in Europe now that are using aerogels for carbon sequestration to reduce the carbon footprint. They were used as radiation detectors in the early 60s. And people like NASA and sort of the Parker Solar Probe mission has a huge carbon aerogel heat shield on the front of its equipment to protect it from the sun. So it's fabulous, has fabulous insulative characteristics as well. So and JPL also have used it as cosmic dust collectors, which will, which is a sort of a fun aside, but they're wonderfully diverse materials, and yeah. So our application initially has been working with removing lead from water. Now we're starting at very high concentrations, and you can see here that we remove over 50% of this 100 part per million lead 2+ in ultra pure water. A lot of this occurs in the first 60 minutes, just a sort of a batch absorption method, so nothing fancy. We did some other analysis with different valencies to see the comparisons, some temperature comparisons too. But the key thing is, we're getting 500+ milligrams per gram of absorption of lead, in these high concentrations. So, when we bring it down to relevant environmental concentrations, your aerogel filter is going to last you a long time. This is our hoping. So, and our kind of rough idea of how this is, what's the mechanism behind this, and we think pretty much it's the design exchange that goes on. Design exchange, because we can see the calcium being chucked back out. We can see that the calcium is lead, and then we've got the van der Waals forces that are happening with the lead attaching to the graphene oxides, and there's a potential for some quantum tunneling of the protons as well, that are creating vacancies between the graphene oxide layers, because they're not all fully dispersed into single monolayer flakes. So this is really interesting. So our oil water applications, now the great thing about the cross-linked nature of this oil, the aerogels, is that they're robust. I mean, they can support. In here we have two 50ml syringes. We just have a couple of bulldog clips, the aerogel just sitting there clamped, so it's self-supporting. And we did a little bit of little video here. So we've got some commercial rapeseed oil, dyed it with Sudan red, just to see the difference here. It's not mixing here, oil water, obviously, you know, and it's not an emulsion, I get that. But when you pour it in, we get an initial mixing, and then the columns start to separate, and you can see the water at the lower end here. Now this water's, but as you look, you can see that the water is filtering through. There's, you know, the aerogel itself is oleophobic, but it's hydrophilic. So it selects for the water, allows that to pass, and due to the control of the pores, the functionality of the actual surface of the aerogel is preventing any of the oil passing. So, you know, this is a really, really, really good example of how aerogels can separate from oil, which, you know, happens in natural disaster. Also, it's happened due to industry as well. In some places, and you can see the last, is that the last drop? Yep, there it is, and it's holding up the oil column. So there's robustness in the structural integrity of graphene oxide when it's cross-linked, and a similar. This is another point for me. DI and crude oil this time, so much nastier. A collection of hydrocarbons here, you know, lumpy bits. There's nothing, you know, beautiful about it. With some DI. And as you can see, all the crude is sticking to the outer surface, you know, of the bridge there. Similar process of is filtering through, nice and clear, and you know, small scale, admittedly, but you know, very effective. Oh, we've landed on Mars. There we go. That's my voice from the video. So oil and water separation, fabulous application. Another application we tried is the absorption of methylene blue. We did serial dilutions of methylene blue, and here you can see the blue tinge of this is a polyacrylic acid and graphene oxide. This was a different sort of polymer for absorbing the methylene blue. We got a 600 milligram per gram absorption capacity with it, and you can see here it's just me prodding the aerogel. It's robust, it doesn't fall apart, and the water, and you know, and in after it's absorbed the blue dye, you can squeeze it, and it doesn't, you know, it doesn't then release it back to the environment, which we know is important here. And then we also made sort of RF carbon-based aerogels, which you know, in themselves, resorcinol and formaldehyde is the kind of the precursor carbon material, and then this was then put through you know, high temperature inert carbonization, and you end up with a monolith like this, which, you know, has a kind of an sp2 hybridized conductive network. So this is a conductive aerogel, and this application, this is not our data, but we made the aerogels and did some micrographs of them just to see how the structure comes out. And but you can see here, as you apply a voltage, the positive cations and negative anions are drawn to each side of the graphene aerogel monolith, and you can see that, you know, there's a reduction in the conductivity in the actual solution as it run through this microfluidic channel. So this is great for like a low saline environment. It's not quite full reverse osmosis conditions, but it's low energy. So if you've got a solar if you've got a solar setup, you can power something like this. And the great thing about it, if you reverse the potential, then you can then wash out your structures and then reuse them. So this is a kind of this regeneration thing is really important in this thing. So these are the applications that we've been working towards. And then there are those very cool applications that we won't get anywhere close. Apart from we met some of the team from JPL, and they discussed with us about their star dust collector, which I always find just a beautiful looking object. And it's a little bit like a cosmic pillow for cosmic dust, and as the dust hits this very low density solid, it slows down and is captured without being damaged. And this is, you know, just another strange and peculiar application that some of these low density solids can sort of yield, really. So you know, aerogels are our thing here at Plymouth at the moment. We're really excited about creating some gravity, low-cost gravity filter for removing toxic metals from water. There's a micrograph here of some of the pores in our aerogel structures, and you can see how, you know, they're a uniform, roughly uniform pore. We're going to then pursue the oil and water separation thing, and we talked a little bit about the microplastic issue, and we're thinking of the oil and water separation as a kind of adjunct to solving microplastics. So that's also in the pipeline. But I think, did I start at quarter past? I think I did, and it's 14:45 over here in the UK. So I think that's the end of my talk, and I would like to thank you all for coming, and it's been a pleasure to talk to you. And I would also like to thank Grace at VIT and her team for this great opportunity in such a strange time. So thank you all, and welcoming any questions. Thank you very much.
Thank you, sir. Now some questions from participants, sir.
Yes, sir.
Yes. Sir, what about the mechanical stability of these aerogels? Are they elastic in nature?
Are they, sorry, in nature?
Yeah. Are they elastic in nature?
Oh, they're
elasticity.
Yes, our particular biopolymer aerogels, they are. I mean, you can, if you think of a standard polyurethane sponge that you can get from any commercial, and you know, or even a sea sponge, and you fill it with water, the pores, and you squeeze it, and the water. This aerogel functions in exactly the same way. So it's highly elastic, it's robust, it can be squeezed, it can be twisted, it can be pulled. So there's not a robustness issue with this particular brand of biopolymer aerogel. The typical silica aerogel are very, very brittle. You've seen these blue smoke things, they're like glass, you know, and as you touch them, and they can crack and things like that. But this advent of biopolymer and other composite aerogel materials. Yeah.
So one more question. How can we control the pore sizes of the aerogels? Can we synthesize aerogels without any cross linkers?
Without any cross, well,
yes.
The cross, I would say that the pore sizes are all kind of, they're all dependent on your precursor chemical composition. So if you're using something like resorcinol and formaldehyde, and you make a sol gel out of this, depending on the quantities of your chemicals, your pores will change, your pore size will change. The size of your nanomaterial that you may want to add in there will also change your pore size. The time that you age your sol gel, that can influence the pore size. And you can make pure graphene oxide aerogels without any cross-linker for sure. But they're not as robust as using some sort of polymer cross-linker. So we prefer to utilize natural, you know, pectin, cellulose, alginate, cross-linking materials to improve these nano-functional materials.
One more question, sir. Is it possible to prepare aerogels from polysulfone to remove heavy metals from the environment?
Polysulfone.
Yes, sir.
Yes. I would say you can make aerogels from most polymer materials. I would be maybe just concerned about the secondary pollution that you're going to put out there as a result of the type of polymer that you use. So I would, you know, I haven't done it personally, but I would say yes, but be careful that you don't create more pollution.
Now I requesting ma'am for conclude the session.
So thank you, Johnny. It was indeed a nice presentation on aerogels. So thank you once again for accepting our invitation and delivering your talk. Yeah, maybe see
Great.
you in another.
Thanks.
Yeah, thank you.
Yeah,
Thank you so
lovely.
much.
Thanks
Yeah,
very
yeah.
much. Thank you, everybody.
Thank you. Have a great day.
Thank you.
Yeah, have a
Thank
great
you.
day. Bye.